Welcome to The Explainer. Let's talk about machine learning. And no, it's not just something out of a sci-fi movie. It's actually all around you every single day in ways that might totally surprise you. So today, we're going to break down what it really is, how it works, and yeah, why it's such a game changer for our world. At its heart, machine learning isn't magic. It's really just about this, giving computer programs the ability to learn from data. Think about it. Instead of a programmer writing out step-by-step instructions for every single possible scenario, we build systems that can spot patterns for themselves, make their own decisions, and get smarter over time. They literally adapt. All right, so what does it actually mean for a machine to learn? Let's get into it. And spoiler alert, it's not about robot consciousness or anything like that. It's all about recognizing patterns in data and using those patterns to make some really smart predictions. Okay, so think about an animal in the wild, right? It learns which foods are safe to eat through trial and error, through experience. Well, ML models do something kind of similar. They learn from the data we feed them. So instead of a human programmer having to hand code a giant list of every possible spam word for your email filter, the model just looks at thousands of emails and figures out what spam looks like all on its own.
Okay, now machines can learn in a couple of fundamentally different ways. And this brings us to probably the most crucial distinction in the entire field.
People often mix up machine learning and traditional statistics. They're definitely related, but their main goals are different. Think of it this way. Statistics is often about understanding the relationship between things, like why are house prices going up? It's about explaining. Machine learning, on the other hand, is usually all about predicting. It doesn't care as much about the why. It just wants to give you the most accurate prediction possible, especially when you're dealing with mountains of data.
So, supervised learning is like studying for a test with flashcards that already have the answers on the back. The model gets a bunch of data that's already labeled correctly. This is a cat. This is a dog. It learns by example. Unsupervised learning is the complete opposite. It's like I hand you a giant, messy pile of photos and just say, sort these into groups that make sense. You have no instructions, no labels. The machine has to find the hidden patterns all by itself. All right, so what are the actual tools that make all this happen? Let's peek into the toolbox and look at a few key algorithms. And don't worry, we're going to skip the heavy math and just get the main idea. We're just going to touch on three really popular approaches. One that basically asks a bunch of questions, one that's really good at drawing lines, and one that's an expert at finding hidden groups. First up, the decision tree. This is exactly like a game of 20 questions. The model learns the most efficient series of yes or no questions to ask to figure something out. So to classify an animal, it might learn to ask, does it have feathers? And then, can it fly? Each question splits the data, creating this tree-like path to the final answer. Next, we've got the support vector machine, or SVM. Now, its goal is pretty simple. Draw a line to separate two groups of data. But here's the clever part. It doesn't just draw any line. An SVM finds the absolute best possible dividing line, the one that creates the widest possible street, or margin, between the two groups. This big buffer zone makes it way more confident when it sees new data. And then there's k-means clustering. This is our unsupervised workhorse. Remember that pile of photos with no labels? This is the algorithm for that job. It's all about finding those hidden groups. For instance, a company could use it to automatically segment its customers into different types based on their buying habits without knowing those types beforehand. You just tell it, hey, find me 3 groups. That's the gay. And it goes to work. Okay, so we've built a model. Awesome. But how do we know if it's actually any good? And this is a huge question. I mean, what's the point of a model that's a genius on all the old data it's already seen, but then totally fails the second you show it something new? That's useless, right? We call that overfitting. It's like it memorized the answers for the test instead of actually learning the subject. So to solve this, we do something really smart. We split up our data. Think of it like this. The training set is the textbook the model studies from. The validation set is like the practice quizzes we give it along the way to see how it's doing. And finally, the test set is the final exam. It's data the model has never, ever seen before, and it gives us a real, unbiased grade on how well it actually learned. So how does a model actually learn during training? Well, it uses something called loss. You can think of loss as basically a penalty for being wrong. Every time the model makes a prediction, we calculate how far off it was from the real answer. That's the loss. The entire goal of training is for the model to tweak itself over and over again, trying to get that loss number as close to 0 as possible. Okay, let's bring this all back down to earth. How does this actually connect to your world? Why does any of this tech matter to you?
I mean, seriously, it's everywhere. From the spam filter in your email that just knows what's junk, to the recommendation engine that suggests your next favorite show, to the fraud alert from your bank that saves you from a headache. All of these are models running behind the scenes in basically every industry you can think of.
And the ultimate payoff here isn't just about making better predictions. It's about augmenting what we can do. It's about automating the boring, repetitive stuff so that we humans can free up our brain power to tackle the bigger, messier, more creative problems.
So this all brings us to a final, pretty cool idea. There's this thing called the no free lunch theorem in machine learning. And it basically says there's no single magical algorithm that's best for every problem. So if there's no master algorithm, what's the most important ingredient? When you think about it, if the machine's success completely depends on the problems we choose for it and the data we give it, well, maybe the most critical part of the whole system isn't the algorithm at all, but the human intuition that's guiding it from the start.